Let's get a full screen here, up and running. Hopefully it won't be blurry. Most of the videos seem to be blurry in the first minute or two lately. But let's have at it. All right, so the goal of this video is to be able to take a differential equation of this type with an initial condition and be able to solve it in 5 seconds. A lot of problems in mathematics, if you take your answer, put it right underneath the original question, you can sort things out, see patterns, and just answer a lot of questions quickly and easily. And that's what we're going to hope to do here. I'm also hopefully going to give a little explanation about what's in the parentheses here as to what you're looking at. And going to be helpful if you knew how to put a exponential equation into graphing form. I'll do that for you here from scratch in a moment. And if you knew your rules of logarithms, this video is going to use some of those rules. We're also going to talk about taking an exponential function, generic case a b to the t plus c, and convert it into e notation, because that's what you see on the College Board test quite often. And so we'll have at it. So here's an exponential function, just some random numbers, and understanding the base of an exponential function is all about the ratio of differentials. So how do you get from 5 to 12? You got to go up 7 units. How do you get from 5 to 21? You got to go up 16 units. And you can see how to write that. You start with the asymptote, you talk about the first differential, and then you get the ratio of differentials, second divided by first, and making 0 and making 1. You can plug in 1900 and see how this works. You can plug in 2024 and see how this works. And got some videos on the channel that help you learn that skill. All right, so moving down the board, trusty cart. I think the easiest exponential function is the doubling function to understand. So doesn't hurt to talk about t values here. Going to negative infinity, and as I go to negative infinity, if I'm doubling something to the right, then I'm cutting in half to the left. And if I keep cutting that differential in half, I'm going to 0. Looking at rate of change, zooming in at 2 raised to the 1 gets us 2. 2 raised to the 1 gets us 2. But I'll just make a little bit of change here. 1.001 gets us 2.00138, 5 decimal places. I'm sure there's more after that, but that's what showed up on Google. And looking at the rate of change, 0.00138 divided by 0.01 is 1.38 to 1. Roughly, it's an approximation. It's an approximation. Calculus, you want to take derivative. If you're studying calculus right now, and I guess you need to be if we're talking about a differential equation. It's the ln of the base times the original exponential function. And I have my students memorize some values. The ln of 2 is approximately 0.7. And so therefore, what does it mean? The rates of change are 7 times 0.7 of the y values generated. Well, here's some y values that are being generated. Let's do 7/10. Here's 7/10 of that y value. There's 7/10 of that y value. Whatever this differential is, there's 7/10 of it. Maybe there, and we can start to see 7/10 of this one. We can start to see the outline of the derivative. All right, all well and good. Let's keep going. Now, what if I were to drop this exponential function down 10 units? Well, it sits underneath the original one. Those rates of change, let's get this out of the way. All right. I was doing this video before and I ran into some trouble. And so I'm doing it again. So rates of change, you zoom in at any location, I think we can see that the rates of change are the same. And yeah, if you take the derivative of this, it's exactly the same as the derivative of that, because derivative of the constant is 0 That's constants don't change. And another name for this function in the box, another name for 2 raised to the t is, bring the 10 to the other side, y plus 10. So the rates of change have lots to do with ratios of one. The base of an exponential has everything to do with a second differential on the right divided by a first differential on the left. So therefore, its rates are also a ratio of the rates of change I'm not quite sure how to say this. So we can see it, right? Right. So these rates of change are based on the differential, and it's easiest to measure the differential from y equals 0. Okay. So let's say that when you see statements like y plus 10, we're adjusting an exponential function with an asymptote at -10. That's what I'm seeing here. Right? Remember we said 2 to the t could have been y plus 10. And I didn't have to have k, I could have some function here. Okay, but it certainly has everything to do with adjusting the sizes of the differential with a little bit of multiplication here. All right, so now how do we change exponential functions into E notation? How do we take something like this and get it into the AE to the KT plus C format? Well, you have to know some values. E to the this gets us that. And we certainly know that e to the 0.7 now is another name for 2. All right, and so that could be 2.1. 0.7 times 3, 2.1. So this is approximately the same as 2 raised to the 3t minus 10. Approximately the same. And of course, 2 to the 3 is 8. So this is another approximation of our original function. Okay. So what is 2.1? It's really the ln of 8. Now it's exact. Right? E to the ln of 8. Ln of 8 is what value of the exponent you put on top of e to get 8. Well, I'm putting it on top of e, so I get 8. I guess I don't have to show that. I just talked about it. So we're really here right now. And, you know, so there's a way to get any exponential function in E notation by using the ln function. All right. All right. So where am I at next? Okay. So I guess that function can be written this way. And if you take the derivative of that, the derivative of an exponential function is itself, so that's over here, okay, times the ln of the base, that's here, times the derivative of this linear function. Remember, ln of 8 times t is very much similar to 2.1t, which is just a linear function. And the rate of change of a linear function is its slope, which is there. Now, the nice thing of changing things into E notation is the ln of E is 1. So it's its own derivative. E to the what? Ln means E to the what? Gets us the exponent on top of E in the parentheses, which is a 1. So it's got that what has to be a 1. All right. So I think I played with, before the first attempt at this video went awry, I think I plugged in some values. Again, showed how to change 8 into E notation. Approximation, of course. But you have to have a feel for numbers. And so just to recap, we started with 2 to the 3t minus 10, just this exponential function. We dropped it down 10 units. So it's dropped down 10 units, but the rates of change at any instant are the same. The rate of change at 0 for this function is the same as the rate of change for 0 at that one. Okay, so let's get an initial condition. So if we plug in 0, 2 to the 0 is 1, 1 minus 10, -9. And And we've got ourselves a differential equation here. And remember what 2 to the 3t was, it's y plus 10. And we've got the ln of 8, right? Because the 3 could have been moved inside the parentheses. It's the same thing, proving that over here. Right? Proving that over here, you're really doing 3 times 0.7, which is 3 times the ln of 2, right? And what does this come from? Comes from 2 to the 3, which is the number 8. Those are identical statements. All right, so now the mechanics of solving. This is where you need your foundation of inverse operations. We'll separate the variables. Bring the y plus 10 to this side. We'll integrate both sides, creating c's on both sides, which will move to the right. I'm going to take a little liberty here. I'm not going to do the plus minus. We already know we've got an exponential growth. So we'll just stay on the positive side of things. So ln of y, absolute value of y, take e to the, right? So we're going to move e to the other side. And this is what was on the other side. So I'm doing e to the that. There it is, right there. Okay, and an exponent plus another exponent on top of a base. Let's do an easier one. M squared. M to the 2 plus 4 means m squared times m to the 4. All right, so we have a multiplicative conversion here of e to the c. I guess I'll show it right here. So this could have been written as e to the ln of 8 times e to the c, and we're going to call e to the c a, and that's an amount. Okay, and it's constant, right? E to the c is a number, some number, which we're going to call a. And now we're kind of in the e to the kt, and bringing the 10 over, positive 10, comes over here to be negative 10, right? Now we got that e to the kt plus c format. All right. Let's go over here now. And I guess I don't need to do this. I just did this so I can skip down to here. All right. So if we put a 0 in, 8 to the 0 is 1. All right. And 1, we've got to get this equal to -9 when I plug in a 0. So if this is the number 1, I guess I'll put it here. 8 to the 0 is 1. Then I have to do what? Leave it as 1 in order to get -9. And so that's our a value is 1, which I don't have to write. And we're back to where we started from, which was here. All right, so what if we summarizing a little bit, and then we'll do a couple of practices where our goal was to have an exponential equation and see if we can answer it in 5 seconds without any work. I think I'll do one more for you here, and then we'll tackle 2 problems at the end, give you a chance to just write your answers in 5 seconds or less. All right, so we've got vertical lengths of the differentials, right? We're going to use to measure those differentials from 0. So when I see something like y plus 5, I know I've got an ae to the kt type problem minus 5. I know that's got to happen, right? Because I'm adjusting my asymptote to 0. All right, so let's separate the variables and see if we can get back to this. And then we'll do a couple of problems over there where I give you the differential equation and see if you can just answer it. All right, so let's separate our variables, dy over y plus 5, which could have been written as 1 over y plus 5 dy. Maybe that helps you see the integration on this side. And this one is going to be 2t dt. All right, and that's going to give us the ln of the absolute value of y plus 5, which I'll take some liberty with in a second. This one's going to get us t squared plus c. I hope you can see where I'm headed now. So e to the, on the other side, will get us y plus 5 equals e to the t squared plus c, when we know that that becomes y plus 5 equals a e to the t squared. And let's take the 5 and move it over and make it minus 5 now. And let's put a 0 in. E to the 0 is 1. Okay, but what minus 5 gets us -3? I think I need this to be a 2. Oh, yes. Right, the mechanics take us there. All right, so now let's do two problems here and see if you can just answer quickly. And usually it takes a couple of days of practice, going through this for, 3 or 4 minutes a day early on, then 2 minutes, then 1, then you get it down till you don't have to work. So you put in the effort. All right, so what do I see? I see a 0 gets me 10, and I know I've got an AE to the KT plus 7, so I know A has to be 3, E to there's plus 7, and we're going to integrate 2t cubed, so that's what, t to the 4 over 2. Okay, so there's my function. Don't have to do any work. Not if you understand the component parts to the process. Now, what's this graph look like? Well, that's interesting too. I see a exponent that's not going to generate any negative numbers. So I'm going to look at t to the 4th graphically, which is a very low parabola until I get past the number 1. And so it looks like an even function here. All right, so my graph is going to be, oh boy, e to these y values, as the y values come at me very, very quickly and they're large, this is going to go up very fast on this side, and it's also going to go fast on that side. So I've got an exponential function that actually looks a lot like this. So what would it be on the left side? So if we were on the left side of this exponential function, which is not going to 0, so there's no asymptotic behavior, really. So this is just put a 0 in, I'm at 10. So I don't think I can get any lower than that. And it looks like it's almost coming over flat and then really, really climbing. That's what I think is going to look like if I put it in Desmos or put it in a graphing calculator. I think it's going to look like that, which means that if I take, even a small negative number, here's your x-axis, your t-axis. Even a small negative number like -2 should be coming down like a, oh my God, I don't know. Something very fast. Yeah. We got to get out there for grandma. 2 hours ago, she's heading south and whoo, going like a bat out of heck. All right. So let's put -2 in, and then let's put -2 here. So -2 minus 7 is -9. All right. And let's see. Oh, I got to do the y value at -2. The y value at -2. Oh boy. I'm going to do that. So the y value, I have to get this because this is so 16 e to the 8. E to the 8 times 3, 24. 24 plus 7, 31. Ooh, 31. So anyway, so -2 cubed, -8, -16. So I may have blown this out of proportion, but that's a pretty negative velocity here. Right? And I'm not even sure that I didn't butcher that by e to the, I think I just did. E to the -2, e to the 8. What the heck is e to the 8? It's not that. It's not that. E to the 8, 2.7. 1 times 2.71, 8 times. Oh, okay. Big number, big negative number, kind of confirms that I'm going down pretty darn quickly, pretty quickly right there. All right, let's try another one. All right, so you're looking at that, you're pausing the video. Let's say 0 gets us 7. All right, 0 gets us 7. And so therefore I know that I've got an A, E to the KT -3 situation. So if I want 7, I can see A is 10. Now, and 2 cosine t, if I integrate 2 cosine t, I believe I get 2 sine t. So that should be our y. We can hopefully take the derivative. So y prime, shortcut notation for dy dt is equal to itself. 10 e 2 sine t times 2, chain rule, times the ln. Oh, I'm taking the derivative, excuse me. So that's going to be cosine. I got to take the derivative of that, which is 2 cosine t times ln of e to the 2 sine t. What is e to the 2 sine t? It's adding 3 to this side So the exponential function right there, right? It's gonna be y plus 3 on this side. And so I could take that right here and call it y plus 3. Take the box and call it y plus 3, right? Boom. And that's where we were to begin with. So if you're on a standardized test and you understand the process, multiple choice, you don't have to show your work. You can save your time for other more challenging questions by knowing what's going on. All right, so I hope that gives you a little feeling for what's inside this parentheses. It's about the adjustment of the differentials. And this can be a function, doesn't have to be a constant, so that you can get more challenging graphs generated. And hope that maybe helps somebody who's studying those differential equations. All right, so let's say, see you later.